Welcome to Multivariate Calculus. Today we are going to explore one of the most elegant and powerful tools in mathematics, known as Lagrange multipliers. Imagine you want to find the absolute best outcome, like the highest point on a mountain, but you're forced to stay on a specific winding trail. How do you find that peak without breaking the rules? That is exactly what this technique allows us to do. Let us dive in and see how it works. Now that we know our goal, let us define what this means mathematically. The method of Lagrange multipliers is used to find the local maxima and minima of a function. But with a catch, we are subject to a strict equality constraint. Think of our main function, f of x and y, as the elevation of a mountain range we want to maximize. The constraint function, g of x and y equals a constant k, is the specific trail we must walk along. We are no longer looking for the highest peak everywhere, but the highest point that lies exactly on our trail. To understand how we find this specific point, we need to look at level curves. These are rings showing where our main function has the exact same value, just like contour lines on a topographic map. If you walk along the constraint curve, your elevation keeps changing as long as you cross these level curves. The only way your elevation stops changing, meaning you have hit a maximum or minimum, is if your path runs perfectly parallel to a level curve. At this exact touching point, the two curves are tangent, and their gradient vectors must point along the exact same line. This geometric tangency leads us directly to our core formula. Because the gradient vectors point along the same line at the maximum or minimum, we can set them equal by introducing a constant. We say the gradient of f equals lambda times the gradient of g. Here, lambda is our Lagrange multiplier. It simply scales the constraint gradient so the two vectors match perfectly in length. In practice, we break this single vector equation down into a system of simpler equations, matching the partial derivatives for the x direction and the y direction separately. Before we calculate anything, let us see this tangency visually. Look at the concentric circles representing the level curves of our main function, increasing from 10 to 30. The red line is our constraint curve. Notice how the red line crosses the curve for f equals 10, meaning we can still move along it to reach higher values. But at the exact point where it touches the f equals 20 curve, it is perfectly tangent. You cannot reach a higher level without leaving the red line. At this spot, the black gradient arrows point in the exact same direction. Now that we have seen the geometry, let us apply this to a practical problem. Suppose a farmer has exactly 10 meters of fencing and wants to build a rectangular pen with the maximum possible area. We want to maximize the area function f of x and y equals x times y. Our strict rule, the constraint, is that the perimeter must be 10. So g of x and y equals x plus y equals 10. To use our method, we first need to find the partial derivatives of both the area and the perimeter with respect to x and y. Continuing with our setup, we take the partial derivatives. The derivative of the area with respect to x is y, and with respect to y is x. For our constraint, the derivatives are simply 1 in both directions because adding a meter of width or length uses exactly 1 meter of fencing. Plugging these into our Lagrange equations, we get our first equation, y equals lambda times 1. Our second equation is x equals lambda times 1. We now have two separate equations that both equal the exact same unknown multiplier, lambda. Since both x and y are equal to the exact same lambda, they must be equal to each other. This tells the farmer that the pen must be a perfect square. We substitute y with x in our original constraint, giving us x plus x equals 10, or 2x equals 10. Dividing by 2, we find the width x is 5 meters. Since y equals x, the length is also 5 meters. The maximum area is 5 into 5, which gives us 25 square meters. We have mathematically proven the optimal shape. Let us tackle a slightly more abstract geometric problem. Imagine a hyperbola defined by the equation x times y equals 1. We want to find the exact points on this curve that are closest to the origin. To make the math easier, instead of minimizing the square root distance, we will minimize the square of the distance. So our main function f is x squared plus y squared. Our constraint function g is x times y, and our constant k is 1. Just like before, our first step is to find the partial derivatives. Taking the partial derivatives of our distance function, we get 2x for the x direction and 2y for the y direction. For our constraint, the derivative with respect to x is y and with respect to y is x. We set up our Lagrange equations by setting the f derivative equal to lambda times the g derivative. This gives us our core system. 2x equals lambda times y and 2y equals lambda times x. These equations look very symmetric, which gives us a hint on how to solve them. To solve this symmetric system, we use a clever algebraic trick. We multiply both sides of the first equation by the variable x, which gives us 2x squared equals lambda times x times y. Then we multiply both sides of the second equation by the variable y, giving us 2y squared equals lambda times x times y. We did this intentionally to force the right side of both equations to contain the exact same term. By making the right sides identical, we can easily connect the two equations together. Because both 2x squared and 2y squared equal the same thing, they must equal each other. Dividing by 2, we see that x squared equals y squared, meaning x must equal positive or negative y. If we test x equals negative y in our constraint, we get negative x squared equals 1, which has no real solution. So we must use x equals y. Substituting this gives x times x equals 1, so x squared is 1. Taking the square root, x is positive or negative 1. This gives us our final closest points, 1, 1 and negative 1, negative 1. Having solved these problems, it is worth noting that this method is incredibly important across almost every field of science and engineering. In economics, it helps maximize a consumer's happiness within a strict financial budget. In physics, it finds the natural resting points of particles constrained to specific surfaces, as nature always seeks the lowest energy state. In engineering, designers use it to find the strongest possible bridge structure while using a strictly limited amount of steel. Optimizing real-world systems with strict limitations relies heavily on this mathematical tool. Let us review our key takeaways. Lagrange multipliers allow us to find the maximum or minimum of a function when forced to obey a strict rule. By setting the gradient of the main function parallel to the gradient of the constraint function, we find the exact points where the two curves are perfectly tangent. This powerful technique transforms complex restricted problems into a simple system of equations that we can solve step by step. You now have the ultimate tool for making the best possible choices under strict limitations.